Let's take a look at some code. Maybe it will help you understand it even more. Let's begin with actually declaring the table. It looks like this. We have this mul table, which is the label we are going to use, and now we define a table of dwords of size width times height. We can, for example, assume that width is 4 and the height is 4. This is what we are going to do in this example. And I want to remind you that we begin counting from 0, which means that we are going to have a pretty strange multiplication table with the topmost row containing only zeros and the leftmost column containing only zeros. But this is just an example, so bear with me here. This is the code for filling in the table. Don't be intimidated, we are going to check it out instruction by instruction. We are going to fully understand it. Let's take a look at what we can see here. First, there is the initialization. We move this label mul table into ESI, and we also initialize two counters, one for the rows and one for the columns. Those are ECX and EBX. The next thing that we immediately see is that there are two loops here. One is internal, which is called next column. We can see this instruction, jump not 0, which jumps to this label, next column. And the other loop is external. It is called next row. We can see this instruction, jump not 0, which jumps to next row, to this label. Basically, we have a loop inside the loop. Now, we should only find out how many times each loop happens. And this is pretty easy in this code. We can see that the only thing that increases here by 1 is EBX. So EBX, which is the column counter, is probably the inner counter of this loop, of the inner loop. We also see that we compare it with width, and that it is initialized to 0 before the loop begins. We conclude that the internal loop is going to happen exactly 4 times, because we know that width is of size 4 in this example. By looking at the external loop, we can see that this loop also iterates exactly 4 times. And we can see it because the counter of this loop is ECX. It is compared to 4 in every iteration, and we only exit the loop if we get to 4. And ECX is initialized to 0 before the loop begins. So basically, the outer loop iterates 4 times, and for every such iteration, the inner loop iterates 4 times, which gives us a total of 16 inner iterations. The code inside the inner loop, which is in this case most of the code, is going to be invoked exactly 16 times, which is pretty cool. We made this construct using 2 loops, one loop inside the other loop, that allows us to iterate 16 times. And I remind you that 16 is exactly the size of the table. It is exactly the amount of dwords in table, or maybe the amount of cells in this table. So we somehow expect that these 2 loops are going to iterate over all the cells inside the table in some smart way. I want to show you how it looks like. I don't want to talk too much about the code. I want to show you what happens when we run it. You will have time to look at this code later by yourself. We begin with this instruction, move ESI mul table, which sets ESI to actually be mul table, and I added this syntax just to help us understand what actually happens here. Next, we initialize ECX to be 0, and I mark it like this. ECX is just some kind of pointer to the row number, and EBX is some kind of pointer to the column number. Instead of just writing their numbers, I draw them like this. Next, we have those 3 instructions, which, as you can see, I've skipped because I don't want to execute those every time here because it's quite boring. Let's see just once what those 3 instructions do. They take ECX, multiply it by EBX, and store the result inside ESI. ESI has the job of pointing to the current cell. And currently ESI points here to this cell. By the way, the numbers that you see here inside those cells are not what is going to be inside the memory. They are just the numbering, so you can understand. Whenever ESI is 0, for example, it means that it points to this cell. If ESI was 10, for example, then you know that it points to this cell. Those numbers are just a reminder for you that this table has this representation in memory. It begins from here and then follows here and here and here. Because this table is just how we interpret the memory, but it is not the way it is stored in the memory. This is just an idea. Let's move on. Next we move 4 to ESI, and this is done so we can point to the next location in table, because after we've done the multiplication and store the result, we want to move to the next location to store the next result. By the way, the result here was 0, because 0 times 0 is 0. So we increased ESI, and next we increase EBX. Currently we have some kind of a synchronization between ECX, EBX and ESI. Almost at any point in the code, the cell pointed by ECX and EBX is the same cell that ESI points to. This is a pretty interesting idea, that ESI is going to do a very strange journey through all this table together with ECX and EBX, and they are always synchronized. Next we check if it is time to end the loop, and of course it is not the time to end the loop. In those 3 instructions, now we store the result of the multiplication, which is going to be 0, and then we increase ESI to correspond to this new location here. And don't worry, EBX is immediately updated so that ECX, EBX and ESI are synchronized, all of them pointing to this cell. So we move on. Everything is pretty much the same. The result of the multiplication is stored here. And now something interesting is going to happen. EBX is increased and now it is of value 4. We actually finished the first row, and now we are going to move on to the next row. And magically ECX has increased by 1. We went outside the inner loop to the outer loop and did 1 iteration. And now we move on with the inner loop again. We are going to iterate over the second row. So basically what happens with this code is that we iterate with ESI over all the table in the following route. We begin with this cell 0, 1, 2, 3, and then we move on to 4, 5, 6, 7. Then we move on to 8, 9, 10, 11, and so on. This is how we iterate over the whole table. And we do it in this special way using nested loop. A loop inside another loop. One loop is for the rows and another loop is for the columns. If, for example, we wanted to switch those two loops, then we would have the transpose representation, which means that we would begin from this cell and move down, and then continue from here, continue from here, and continue from here. About more dimensions. The same techniques apply to more than 2 dimensions. I don't want to talk about it here because it is a bit cumbersome, but you can think about it yourself. There is not much to it. Think about how to translate the XYZ coordinates into a linear memory location. It is just about thinking how to take this cube, which is a 3-dimensional array, and flatten it into this linear memory. This is all it is about.